Jai Hind, dear students. I'm Dr. Preeti Mittal. The chapter that we are going to start today is sound. We hear different sounds in our life, but have you ever wondered at how these sounds are produced? These sounds are produced because of the vibration of the particles. So when I'm speaking, at that time also, the cartilages present in my vocal cord are vibrating, and that only produces the sound. So if we talk about the sound, have you ever seen these vibrations? Because I can't see my vocal cord. So have you ever seen these vibrations in any of the things that is producing the sound? Yes, you all have seen that. Just recall that when you went for some party and when some loud music was playing, then you can see the movement of the drum of the speakers. Loudspeakers drum is there and that is continuously vibrating. And that's vibrations you can even see because that is very loud music. So you can even see those vibrations. So when it is vibrating, how this sound is propagating? Let's talk about it. Sound waves are mechanical waves. Mechanical waves are those waves which need a medium to travel. So when the sound is traveling, that requires a medium. That is different from light because light doesn't require any medium. It can travel even in vacuum. But sound always requires some medium and it cannot travel in vacuum. That is why we get the light from the sun, but we can't hear the sounds going on in the space. So let's see what is happening when the sound waves are moving, when it's propagating from one place to another, how this propagation is going on. So just suppose we have some particles in the medium. Okay, there are many particles in the air. So suppose the sound is going to propagate through air and these are the particles that are present in the air. And this is the drum of your loudspeaker. Now, when it vibrates, when it comes out, it will come out first and then it will move in. This is the vibration of the drum. So it will once move out and then move in. So when it will move out, it will push these particles in the forward direction. So these particles will be pushed forward and so in a region next to it, there will be area where the number of particles will be moved. So now they were pushed from here and so what will be there? Then the particles in the next area where they will be pushed, that number of particles in that area will be increased. But after pushing it, the drum went back to its original position. It went back there. And so what happened? The particles were all moved there. So in this area, from where it was pushed, in this area, the number of particles will be very, very less. Okay, so where they will be pushed at that particular area, the number of particles will be more, and from where that was pushed, the number of particles in that area will be less. So what happens? There is alternate production of areas of more particles and less number of particles. Alternately, we will see that in the air, in the medium, whatever could be the medium, so the number of particles will be constantly, like one area will be having more number of particles and the next consecutive area will be having less number of particles. So we'll have this kind of a pattern that will be shown by the number of particles. Now the area which is having more number of particles, this area is known as the area of compression. This is the area of compression. And from where the particles have been moved out, this area is known, where the particles are less, this area is known as rarefaction. Compression and rarefaction. So now what will be happening? Since in this area, the number of particles is more, so the density of particles is more. And when the density of particles is more, there is high pressure in this area. So in the area of compression, there will be high density or high pressure. High density as well as high pressure. Why it is high pressure? Because the particles are very much closely packed in that area. So there are a lot of particles in this area. So this area will be having a high pressure and more number of particles are there. So we call it as high density also. But in the area of rarefaction, what will be there? There will be low density because the number of particles is less, and low pressure also because the number of particles is less, so there is not much pressure in that area. So this is the area of low pressure. Now if we plot this as a graph, that the area, how much pressure is there, so we plot this pressure or density as a graph and we take this as a mean position. Mean position means where the pressure is neutral. When the sound is not there, whatever is the pressure, that pressure is taken as a baseline, and we plot the graph for the pressure. Then what kind of a graph will be there? There are areas of high pressure and there are areas of low pressure. Then again high pressure and areas of low pressure will be there. This point will be representing the pressure high, and this point is representing when the pressure is the minimum or lowest, because this is the pressure area what we are representing. And this mean position, mean line here represents the neutral pressure. When there was no sound propagating in the medium, whatever was the pressure of the particles there, that is shown by this mean position line. Okay, so the area of high pressure is represented here, and when the pressure is going to fall down, this is the area of low pressure. This high pressure area is known as crest. When the pressure is maximum at a point, that point where the pressure is maximum, that point of the graph is known as crest. And when the pressure is lowest, that part is known as trough. So the point where there is high pressure and the pressure is maximum, that is crest, and the lowest pressure area is known as trough in our graph. Okay. Now I told you that sound waves are mechanical waves. So what other kind of waves are there? That also we need to learn. That is transverse waves. Okay. Now we'll see the difference between transverse waves and mechanical waves. First talk about mechanical waves. The sound waves are mechanical waves. So in this waves, you can see that the particles are being pushed forward, and once they are pushed forwards, they will eventually come to their own position also. So the particles will be vibrating in a direction parallel to the propagation of sound. The sound is propagating in this direction, suppose, and the particles are also vibrating to and fro. These particles never go from the area where the sound is produced to the area where the sound is being heard. They just transfer the energy from one particle to another. Okay, so suppose if the first particle was getting the energy, that energy will be given to the second particle, then the second particle will be giving the energy to the third particle. In that way, the particles will be passing this energy from one particle to another. The first particle is not going to take the sound wave right up to your ears. Okay, so such waves, when the particles are transferring the energy from one particle to another, so such waves are known as longitudinal waves. Okay, such waves are known as longitudinal waves. Fine. So it requires a medium. So it is a that requires a medium. Sound requires a medium. So it is known as a which kind of a wave? That is known as a mechanical wave. But since the particles are moving in the direction of propagation of sound waves only, so such waves are known as longitudinal waves. Okay, it's just like passing the parcel. The energy is transferred from one particle to another. Okay, you must have played passing a parcel, no? So it's similar to that. Now we will talk about transverse waves. The light waves are transverse waves. What are transverse waves? Suppose if some form of energy is traveling in this direction and the particles are moving just up and down. They are just moving up and down, perpendicular to the direction of motion of the wave. So if a wave is traveling in the forward direction and the particles are just vibrating up and down, that is perpendicular to the direction of propagation of wave, such waves are known as transverse waves. Okay, for example, if you throw a stone in water, then what will happen? The water is going to move up and down. So that up and down movement that is perpendicular to the direction of propagation of wave is known as transverse waves. Light waves are also transverse waves. But remember, light doesn't require any medium. So it is not the particles which are moving up and down in case of light. There are some energy particles, energy photons are there that are traveling up and down. Okay, that you will read in your higher classes. So just remember two things from here. Sound waves are mechanical waves, that is require medium. Sound waves are longitudinal waves, that is the particles are oscillating to and fro, and the direction of oscillation is same as the direction of motion of the sound wave. Okay, now I told you that the sound, when the sound is traveling, only the energy is transferred from one particle to another. Okay, these particles in the medium are not going from one place to another. It is only the energy that is being transferred from one place to another. Remember that. Okay, now we will see about some of the characteristics, features of sound waves. So I'm just going to erase this off. I hope this is clear, but we'll let our diagram be there only, the graph that we have plotted. So one thing that's very important we have seen is the area of compression is the area of high pressure, and the area of rarefaction is the area of low pressure. So if we plot a graph, then based on this graph, we can learn many things. So just we will learn about some of the terminology related to sound waves. These terminologies can come as 1-mark questions for your in your exams as short note as well. Okay. So the first thing is frequency. Frequency describes the number of oscillations per unit time. Means in 1 second, how many sound waves are there? How many compressions and rarefaction? One compression and one rarefaction will make one complete wave. So this is one compression and this is one rarefaction. This complete will be one wave. This complete area which covers one compression and one rarefaction, that is known as complete one wave. So how many waves are there in 1 second? That will give you the frequency. Okay. So the number of waves that are there in 1 second, that is known as frequency. Fine. So that will include, one wave will include one compression and one rarefaction. Fine. Now, pitch of a sound is there. You must have heard that females have a high pitch, male voices a low pitch sound. So this pitch defines the frequency. If I talk about two waves, I'll just draw one more here. Okay. So suppose this is also in 1 second and these number of waves are also there in 1 second only. So in 1 second, how many waves were there in that figure? That was just having two waves. So it was a low frequency sound. But here the number of waves is high. So it is a high frequency sound. So the number of waves that occur in 1 second is known as frequency, and the pitch is also dependent on frequency only. If the number of frequency is high, then it is called a high pitch sound, and if frequency is less, then it is called a low pitch sound. Some examples of pitch doesn't has to do anything with the loudness. Okay, loudness is something different. We'll talk about it. But if we talk about some examples of high pitch sound, for example, a female voice is a high pitch sound. Apart from that, the buzzing of a bee, that is also a high pitch sound. But a lion roar is a low pitch sound. Okay, and apart from that, male voice is also a low pitch sound. Okay, so pitch of a sound is depending only on frequency and it has nothing to do with the loudness. So on what factor loudness is going to depend, we'll see that. But before that also, in frequency only, learn these points also. In your book, there it is given very like at different places. We'll just compile all the topics related to one particular topic at one place only. That will make your learning easier. So what is tone? Tone is a single frequency. So if you hear a voice like this, beep, so it is having a single frequency. The frequency is not changing. So such a voice is known as tone. Okay. And what is a note? When there is a mixture of different frequencies, such a sound is known as a note. So when different frequencies are there, changing frequencies there, then it is known as note. And when it's a single frequency only, then it is known as a tone. Now, if it asks in an exam, how will you remember that, all that? Just remember by one example, just to memorize the thing. Note, when you write the notes, they're always different. Now, sometimes you're writing SST, sometimes Hindi, sometimes in Sanskrit, sometimes in science. So when you're preparing your notes for different subjects, for different topics, they're always different. So note is different frequency. And tone, word only, like sometimes your mother asks you, change your tone. Don't talk to me in this tone. So you don't like a single frequency, single mood. So you are asked to change your tone. Okay, so by that way you can remember what is tone and always writing the notes, these pretty students. So what that is, note is different frequencies. Okay, now we talk about time period. Time period is the time taken to complete one complete oscillation. For complete one wave, whatever is the time taken, that is known as time period. So time taken to complete one compression and one rarefaction, that will be known as time period. Now you can easily think that if in 1 second two waves were there and I called it as the frequency is 2. So what will be the time taken for one wave? It will be half a second. Okay. So frequency and time period are inversely proportional to each other, and frequency is 1 upon time period. So here my frequency was 2. So what will be the time taken for one complete wave? So we can write the reverse also. Time period is equals to 1 upon frequency. So 1 upon frequency means time period here will be half. Okay, in half second, one wave will be completed. The frequency of sound is not so low, but I'm just telling this example to make your things easier. Okay, so frequency and time period are inverse of each other. Okay, higher the frequency, less time will be taken for a particular wave. Here the frequency is high, so each wave will be taking a very less time. Okay, so that is time period, time completed for one complete compression and rarefaction. That is known as time period. Now we will talk about amplitude. We will talk about amplitude because we were worried about the loudness. That I told you that loudness is not dependent on frequency. Then what is loudness? So this maximum pressure changes that are occurring in a wave, this distance from the base position, how much the pressure is changing, that defines the amplitude of the sound. So if the sound waves, suppose I plot another graph and here this is there. The frequency is remaining the same, but the pressure changes are more. The compression and rarefaction is more. Then this dotted line is representing higher amplitude. Okay, so the force with which we are pushing the waves, that will decide the amplitude. If I try to speak louder, then I will be applying more force, and I will be pushing my cartilages on the vocal cord more. So that will be producing a higher amplitude. So the distance between, if the crest and the mean position is more, that means it is a louder sound. Okay, so that is going to define our loudness of a sound. That will be dependent on the amplitude. So the maximum pressure changes that are occurring in a sound wave, that will help you to know its amplitude. Okay. Next comes the intensity of sound. Now this intensity of sound is the amount of sound energy that is transferred, per unit area in a unit time. Okay, the amount of sound energy that is transferred per unit time means in 1 second. What is the amount of energy transferred per unit area? Means the area is 1 meter square. Then that is known as intensity. Okay, the amount of sound energy that is transferred per unit time in 1 second, or you can say in 1 second per unit area, that is known as intensity. Now this intensity of sound could be measured, but this loudness and intensity are not the same, because loudness will depend from person to person. Just imagine an old person. They usually like to hear the sounds at a higher loudness. That sound is okay for them, but maybe very loud for you. When your grandmother watches the TV, you must have observed sometimes, and when she's watching, that depends on the perseverance of the power of the ears, how much they can collect the sound waves. So loudness, that depends from person to person. A voice that is loud for you may not be loud for someone else. Okay, so but intensity is a measurable quantity. You can measure that, and it doesn't vary from person to person. It is the energy transferred in 1 second per unit area. Okay, I hope that is clear to you all. Next comes the wavelength. Wave ki length. It's very easy. So the length of one particular wave, that is the length of one compression and one rarefaction, that is known as wavelength. And this wavelength is represented by the symbol. This is the length of one particular wave, and this wavelength is represented by the symbol lambda. Okay, so this is a symbol, and that is representing wavelength, and its symbol is lambda. Okay, since its length, its unit will be meters. The SI unit of wavelength will be meters. I just forgot to tell you the SI unit of frequency, that is hertz. Frequency is always measured in hertz, H-E-R-T-Z. It's measured in hertz. Time period is measured in seconds because it's time, so SI unit of time is seconds only. Okay. Now we talk about quality or timbre of sound. Quality or timbre of sound is like if two persons are there speaking with the same loudness and same frequency also, then also the quality of their sound is different. For example, quality of sound of Lata Mangeshkar is different from that of Asha Bhosle and very different from that of mine. So that quality or timbre of the sound depends from person to person. That doesn't depend on the frequency. Two sounds could be having same frequency, same loudness, but still the quality of the sound is different. That is, the timbre of the sound is different. And next we are going to do some numericals, but before that we'll learn about the speed of sound. Now, when the sound wave is traveling, the distance covered by the sound wave per unit time is known as its speed. Okay, so you always know what is the formula of speed. You always knew that for whenever we are talking about speed in general, we talk that speed is distance upon time. So when we talk about sound wave, what is this distance? This is the wavelength. The distance covered between one consecutive compression and rarefaction, that is wavelength. And so here when we talk about the speed of sound, it could be given by wavelength divided by time. Now divided by time is equal to 1 upon time period is frequency. So wavelength multiplied by frequency will give you the speed of sound. Wavelength multiplied by frequency of the sound wave will give you the speed of that sound wave. Now the speed of the sound wave doesn't at all depends on whether you are speaking loud or slowly. Even if I speak softer or louder, the speed is not going to depend on that. This speed of the sound depends on two things. Speed of the sound depends on the medium and the temperature. These two things are going to decide the speed of sound. So speed of sound is going to be different for different medium and for different temperatures also. How they are dependent? Speed of sound is maximum in solids and minimum in gases. Okay, so if you want to check that, just if you just put your ears to a railway track. So before you hear the sound of a train coming through the air, before that only you can hear that sound if you put your ears next to a railway track. So the sound travels faster in solid because the particles are very close to each other. So energy is transferred very easily in them. Okay, so the speed of the sound is maximum in solids and minimum in air, minimum in gases. Okay, remember that, very important. Fine, but don't do that experiment ever, and it's very dangerous to do that. Now next thing is temperature. Higher the temperature, more will be the speed of sound because it's the energy. So when the particles are already having more energy at high temperature, the particles will be having higher energy. So it's easier for the energy to be transferred. So so higher the temperature, more will be the speed of sound. High energy, more speed. Solids, more speed. Remember that. Okay. Now, based on this, we are going to practice just two numericals that are given in your NCERT book only, and we'll just practice them. Okay. So I'll read the question for you and just try to do it by yourself. So just let's see how many of you are able to get the correct answer. Just let me know in the comment section. If you were able to do the question by yourself, just give a thumbs up. One question that I'm reading, that is, calculate the wavelength of a sound wave whose frequency is 220 Hz. Now, the symbol for frequency is nu. This is the symbol used for frequency, but I try to avoid that because the symbol used for speed is V, and they look quite similar to each other only. Okay, so it's better to just write the word frequency and write the word speed. Or for speed, you can just use the symbol, so it's clear that for frequency, you are using the word frequency. Okay, frequency is given 220 Hz, and the speed is 440 meter per second. You have to calculate the wavelength. It's very easy. You have to calculate the wavelength. So just putting the values in the formula, speed is 440 is equals to wavelength. You have to find out frequency is given 220 Hz. So wavelength is equals to 440 divided by 220, and that will make it 2 meters. The wavelength will come out to be 2 meters. Very simple question. Let's do the next question. A person is listening to a tone. Tone means single frequency. Frequency is 500 Hz. Sitting at a distance of 450 meters from the source of sound. What is the time interval between the successive compression from the source? So you know that time period is 1 upon frequency, that is equal to 1 upon 500, and that will make it 0.002 seconds. So this 450 meters distance is just given to confuse you. They're just asking you time period, and you know that frequency and time period are inversely proportional to each other. So time period is 1 upon frequency, and that will give you the answer. Fine, everyone? Okay. So that's all for today for this class. In the next class, we are going to see about the next concepts from the same chapter, sound. Okay. Till then, goodbye. Have a nice day.